All right, good morning, everyone, and welcome to today's session for Unicode Research. I'm going to be presenting about graph neural networks, and it's a slightly opinionated review because I don't present everything in the world of graph nets, but try to direct you towards motivations for how graph nets evolved, then the types, largely the types of graph nets, and then we examine in great detail like where and how graph nets don't really match what they promised, in the sense like failure modes. um, and I guess I could summarize it by saying we examine the power of graph neural networks, because that's the term that people use in the literature. Like, what can they express, what can they capture, what can they learn, and what can they not learn, and the specific tests for these kinds of things. With that said, we can start with our presentation. So, why do we care about graphs? Well, for one, they're everywhere. There are many obvious applications that I'll get into, but two of them in particular stand out. The first one being chemistry. So, computational chemistry typically treats atoms and molecules as intrinsic graphs, because atoms are essentially nodes, and combining these nodes, the chemical bonds that allow us to form molecules, um, essentially represent can be represented as a graph. And so it makes sense then that the earliest applications of graph neural networks actually arises independently from computational chemistry. And I'll link to a talk that more carefully lays out the history and development. But for now, let's look at this particular problem of interest, where we want to check whether a particular drug will inhibit the growth or the progression of a certain type of bacteria. So we care about this molecule, and its properties with respect to specifically whether it inhibits E. coli. So I want to predict whether this molecule is a potent drug, which is essentially a binary classification task. So given a drug, predict yes or no, can it inhibit this bacteria? Now we can train it on a curated data set of compounds where we do actually know the response to obtain this GNN model that can do really cool things. So you have a training set of known molecules, known properties. You perform learning with graph neural networks, and then you have this massive test set. So you can imagine that you're not limited in your test data set, at least, because you can simulate any sort of structure for molecules. um, yeah, that there doesn't need to be a reason for this data point to be in the test set, so that allows you to really scale up to a lot of molecules very easily. And turns out, when this was a project by a bunch of researchers at MIT, so they actually selected the top 100 candidates that they predicted, and then tested these 100 candidates out in the lab to find one that turned out to be a very powerful antibiotic. So it's really cool that they could do this without the need. And you have to imagine how much effort it takes to test a drug out. You have to perform randomized controlled trials, you have to examine all sorts of side effects, your population size has to be large enough for the results to be significant, and a bunch of things. So essentially you're saving months and months of effort for each molecule that you predict correctly that could be a potent drug, which is really like a huge deal. And with yeah, I mean, they got their due respect. They published in a really popular journal called Cell. They got a lot of press about their new antibiotic that they discovered. And to be fair, it wasn't like new antibiotic, and this is actually validation for their method. This The drug that they found, halicin, had actually been examined for some sort of diabetic applications, but turns out it didn't have great results in some lab trials, so they never explored it further. So they actually rediscovered this compound in terms of a new use case, which is inhibiting E. coli. And oddly enough, the Financial Times also featured their work. So for me, that was interesting because I didn't think the Financial Times did a science and life sciences and machine learning review. But anyway, the next question that you want to think of is, what am I talking about with this image in front of you here? So it is essentially a screenshot from some sort of maps app, and we are talking about graph neural networks. So the natural question that arises is, where is the graph? Well, if you blink 5 times and chant after me, the traveling salesperson problem is NP complete, then this magical figure materializes on top of your map and you have your graph. So the nodes, to be clear, are these intersections. The edges are these segments of roads between these intersections. And in practice, actually, they super segment these roads. So what is the data set here? Google has a bunch of historical vehicle speeds on each of these segments of roads. In fact, they also have the speed, the time of the day, the direction, and a bunch of other features. So you can imagine that even these single segments, hopefully you can see my cursor, even these individual segments can be super segmented, which is in fact what they actually do. And that gives them this ability to accurately predict ETA, expected time of arrival, or estimated time of arrival. I don't know. But yeah, ETA prediction dramatically improved across the world. So it's not just learning something specific to a certain country in terms of traffic patterns or people's working habits or so on and so forth. It actually works across a bunch of countries. So in all probability, when you look up Google ETA, you're using graph neural network. So clearly they have real and impressive results. And there are many more cool applications that I can get into if we have time later. But for now, let's start our journey with this very simple theoretical idea, um, in terms of like what sort of functions do we want operating on graphs. So if you think about the motivation from convolutional neural network land, if you think about images, each pixel in the image has some neighbors, and then you run this convolutionally. So there is an image which is a matrix of numbers, there is a filter which is a matrix of numbers, typically a smaller matrix than the image. You pass this filter over the image, you learn some features, you do some multiplication, and you pool certain things to reduce the size. Because you're doing matrix multiplication, you want to end up with a single number, you start with millions of numbers. So there has to be some operation in the middle that reduces the dimensionality of this matrix to arrive finally at the single number, which is your prediction, right? So that is sort of the motivation for pooling. Also, if you think about it, you don't look at people's eyes, ears, nose, and like lips separately. You look at people's faces, so as a whole. So it's this idea of compositionality, but we'll get into that later. So stepping back into CNN land, looking at this idea of convolution. So in red on the left, you have your image, a portion of the image. The in blue you have the filter in the middle, and basically red shows where the filter was placed. And green is the output you get by multiplying and adding these, the I star k, I convolved with k. So for each cell you do this, and right, and you obtain this matrix on the right, which as you can see is also a smaller matrix. So you are creating some summaries of the image, and these are what you, um, um, hopefully you want to learn some sort of feature maps which make sense. So yeah, so from this field, the idea emerged that okay, you're sort of aggregating this neighborhood of a pixel. And in CNNs though, you saw the, in CNNs you saw that this operates on images, but what, and this is based on Petar Velichkovich's talk. So what Petar says is images are grid ordered graphs, um, which makes a lot of sense when you think about it. Like there is a pixel above, below, left, and right, for most of the pixels that are non-boundary. So in a sense, it is connected to these four pixels at least. You can think about 8 pixel connections also, but that just complicates things. So why not? It's not necessary to do that. Um, and by 8, I mean like diagonals considered. But either way, like if you think of pixels as grid ordered graphs, pixels still have some sort of arrangement, like a permutation matters. Like if you put your nose on top of your head, that is not going to be a reliable face to detect. Or if you put your eyes on the bottom of your feet or something like that. So the order of these pixels does matter. But graphs, typically in the real world, you don't have order in the nodes. Like you can order nodes in any way. So then the question arises, like then you want two different graphs that look the same, and I'll explain this with an image very quickly. So the graph on the left and the graph on the right are the same graph. So that is what I mean by nodes are not ordered. You can visualize it in any way. You can also consider an operation on it in any way. And so you want your function ideally to give the same output for both graphs because they are the same graph, which means this we want an isomorphism preserving function for arbitrary graphs. um, and at any point in the presentation, please pause me if I'm going into too much mathematical detail that you don't follow. So I'll give it a minute in case someone has questions. Okay, seeing none. This we'll get into this idea again in much detail. It's called the Weisfeiler-Lehman test for isomorphism. And why is there a test? Well, because it took you, like, if at least it took me a second to identify both of these are the same graph. If someone hadn't told me, this is like the description below it is how I would have tried to figure out if they're isomorphic. First, I would check if they have the same number of nodes. If not, then they clearly cannot be isomorphic. Then I would check the neighbors for each node and try to figure out, okay, which ones have like a corresponding number of neighbors. And then finally, I would try to rearrange these nodes by correspondence. So, like, find a mapping that is 1 to 1 from the graph on the left to the graph on the right. And if I'm successfully able to find this mapping, then that's it, I'm done, and I can confirm that they're isomorphic. If I fail, they're not isomorphic. So that's essentially how you check for isomorphism. And if you think of an algorithm to do this on arbitrary graphs have finite countable number of nodes, but those countable number of nodes can be massive, like a huge number. And doing that in polynomial time is impossible as of today. There is no polynomial time algorithm that can check for isomorphism of any two arbitrary graphs. But there is one test that approximately solves this problem, and it works for most real world graphs, which is to say it has very few corner cases observed in practice. So that test is called the Weisfeiler-Lemon test. And I'll get into the details in a bit, but this is the general idea. Like, first thing we want to do is check for isomorphism, and we want this isomorphism preserving function. So that's like we care about these translation invariant, by which I mean, no matter where in the image you have a face, you will identify it as a face. So your kernel and your approach is translation invariant, which means if you translate a feature somewhere else in the image, the kernel will still detect it. Anyway, so that it translates into this isomorphism preserving function when you come to the graph domain. Um, and so the terminology I'll be using for today is G is the graph. It comprises of some vertices and some edges. X are your node features, which comprises of a set of n nodes, and xi for a feature set for each of them. This hi should have been an xi, so ignore that for now. Xi is belongs to the domain Rf, so it's like an f dimensional feature vector. But it won't be really important to think of things as multidimensional. I'll get to that later. It can generalize easily is what I mean. There is a neighborhood of I. So sorry, before that there is an adjacency matrix, which is an n cross n matrix of 0 and 1, indicating whether two nodes are neighbors or not. So the ijth element indicates whether node I is a neighbor of node J or not. And it is, yeah, symmetric. So neighborhoods Ni is equal to, we're not talking about directed graphs here for now, just for the to be clear. That's why I said the adjacency matrix is symmetric. So if I is a neighbor of J, J is also a neighbor of I. So Aij is equal to Aji. But again, that's not super important right now. We define the neighborhoods of a node, the basically the neighbors that its edges connected to, and the edges Eij are a set of um, indices indicating a source and a destination for that edge. Or yeah, that's probably described a directed edge, but undirected edge just indicates two ends of the edge. So edges can also have feature vectors. So edge features are a thing. Like we spoke about in the road transport example, these edges might have vehicular speeds, time of day, and so on and so forth. So those are f prime dimensional. Again, not super important. We'll get to that later. And there is a degree matrix. So the degree matrix D indicates the degree of a node, indicating how much it is connected. It is typically a diagonal matrix, um, with elements along the diagonals, I think. Yeah. Okay, so the first thing we care about, um, going back to the desiderata for functions. So desiderata is what we want. We want isomorphism preservation, but it starts with this idea of permutation invariance. So if you think about graph level tasks, go back to our drug prediction. At we want to predict at for that entire molecule, is this going to be fighting that bacteria or not? So that is a graph level task. We what we do is we stack all of these node features, and unfortunately by stacking these we do define some order, right? So if we want to say that this method will work on any form of stacking, you have to define multiple different kinds of stackings and show that it works for all of them. Instead of doing that, you can just define this permutation matrix P, such that P times X is actually just X shuffled. So it's an arbitrary reordering of X. So you see these elements have ones, only a single one in one column, um, which means that column will just be permuted to that index in Px, which means that row will be permuted to that index. Oh, column. Hmm. Yeah. Um. Anyway, permutation invariance then mathematically implies that a function operating on a permuted version of X will have the same output as a function operating on X. So no matter how you shuffle around the rows, this fpx will have the same values as fx. Everyone on board with this? I'll pause if there are doubts. Okay, so first we started with CNNs and what functions operate on CNNs. We saw they have some invariances that we like. We transfer to the graph domain. We say, okay, in graphs, we want some sort of similar invariances, but now graphs are not ordered. So we want this permutation invariance. No matter what order of these node features exists, the graph level task output will be the same. Okay. So someone wrote a paper that says, in general, this general example of permutation invariant functions could be of this form. So fx could be of the form phi of summation of psi of these features. And let's break this down. So there are two green values that I'll get to later. First, let's look at this red value, which is really what is breaking this order. So this psi operates on each xi, and then you sum up all of these. And this sum up means no matter what order they are in, as long as psi of xi has a unique value for each xi, or yeah, is injective, 1 to 1. As long as that is the case, then this summation will basically break the invariance. And I'll give you a moment to digest that. This learnable functions MLP is not important right now. Just think of the injectivity, which means one to one, right? Injectivity comes from your basic high school math. Injective, surjective, bijective. Injective is one to one, surjective is on to, and bijective is one to one and on to, I think. Um, okay, so DeepSet's paper says forget the edges in your graph, just treat it as a set of nodes. And for as long as this set of nodes is the same, your function will output the same values. If that is so, this is the class that your function will belong to. And this class of functions can be described. One of these classes is phi of summation of psi of x. So this aggregation is crucial here, and phi and psi can be learnable functions that are hopefully injective. Cool. So permutation invariance then implies that a function applied to these node features f, going back to, okay, so going back to our permutation invariance idea, fpx is equal to fx. No matter the order of the node features, it will produce the same output. This is great for graph level tasks when I don't care about the internal structure of the graph. But if I do care about this internal structure, what about node level tasks? If I have permutation invariant functions, and if this p, now the order matters, right? Now you want at least to know which node was transformed into which value. You don't want to know just one summary number for the graph. So what do? Well, we need something called permutation equivariance, which means a function applied to this permutation of x is the same as a permutation of a function applied to x. And again, take a minute to think about this. What you're saying is the function itself does not reorder the nodes. Function maintains the order. So whether you apply permutation before or after, it is the same. This means if I know my first node is on in the first row, my third node is in the third row, then that will be the case before or after applying the function. Uh, that will be the case whether you permute before or after applying the function. So that matters because now I can examine node level outputs, and say, okay, for this node, this is how it changed. For the other node, that's how it changed. So permutation equivariance and invariance are two things that you need to care about. And interleaving these really gives us these three steps to creating this class of functions. First, let's indicate this hi latent vector as the output of psion xi, right? um, this is like this latent state of a node because you're operating on a node feature. Then we want to stick this aggregator on top. I've replaced this summation with this random symbol that I found, which is actually a multiplication symbol, but ignore that. I really mean any of these operators. Aggregation functions, sum, max, mean, all of these are good for us. So we want those. And then finally, we want a permutation invariant function outside it all, potentially because of these graph level tasks. So interleaving equivariance and invariance essentially gives us really powerful graph level functions. And this generalizes a lot of the work out there which examines independent functions. So with these ideas, we're actually ready to tackle graph neural networks. So I'll pause here before I jump into these slides. I'm asking you folks if you have a clarity on what is the difference between invariance and equivariance. Can someone summarize invariance and equivariance in 2 lines? Okay, can someone try to summarize invariance and equivariance in 2 lines? Come on.
Okay, I'll try. So it's simply like the equations that that you showed made sense. That invariance would just imply that any ordering would just give same output, whereas equivariance would imply that you can get which output matched to which ordering that was in the input. So you can kind of the bijection is retained even in the output for each. So if you have like one match to three, then the output even in the output, the one would match the corresponding output. One would match to three.
Yep, that's basically spot on. So ignoring order and preserving order. That is the difference between invariance and equivariance.
Yeah, but I had a doubt in this slide. So, like in the last equation, put a permutation invariant function outside everything. But this, if you are putting an aggregator, then it's simply
Yeah, I
invariant
think I
function,
meant
right?
injective there. But yeah, yeah.
So the aggregator is not an invariant function, then, right?
No, no, the aggregator is the invariant function. So I think I messed up that slide.
Ah, okay.
So yeah, the reason aggregator is invariant because no matter the order, it sums it all up, right?
Yeah. So then there is no equivariant. So the last phi that is there in the third equation, so that is not equivariant because we have invariant already inside, and now we won't be able to retain. Okay.
Correct. Yeah, you're right. I need to rework the slide.
Yeah. Okay. Thanks.
Yeah, all we care about is injective functions, so that map one value to one value, so that the psi, the hi is injective, and then the external psi, um, I mean, I assume he wrote it this way because of like defining a class of functions. So interleaving was there, or actually I can't speak to that paper because I haven't read it completely. But I know that there are two ideas you want. You want injectivity and you want invariance. And at the node level, injectivity is equivariance.
Yeah, that makes sense.
Cool. So now let's jump to Petar Velichkovich's slides. I should thought I opened them up. Yeah. Okay. Hopefully my screen is still visible. So let's talk about this a little bit. So we spoke about how this operates on sets. For now, I said we ignore edges. Let's just think about a graph as a set of nodes, and for the same nodes, we want the same output. Now let's think about it in terms of edges. So we do have edges. We have this adjacency matrix. We have edge features. We still care about the same thing: permutation, invariance, and equivariance for graph level and node level tasks. And um, once we consider edges, that this adjacency matrix A enters the picture, and we have two dimensions to care about, rows and columns. And so this px translates into pap transpose on the adjacency matrix, which is basically saying like if you permute x, then that is how you permute the adjacency matrix to obtain its corresponding representation. And uh, consequently, the definitions for invariance and equivariance in this 2D case change a little bit. So if you look at this, it's the same idea as fpx is equal to pfx. It's just that you add an additional a term to define how the graph is internally connected. And in invariance, fpx is equal to fx, except there is an additional argument of a and pap transpose. P, if you remember correctly, was the permutation matrix with just zeros and ones, which rearranged the matrix X. Cool. So just generalizing this to graphs. A second thing we care about in graphs is the locality, right? So every node has certain edges, and by consequence a certain set of neighbors around it, and all of these neighbors have features. So what he defines as x sub n sub I, x n I, is this set of features for all the nodes belonging to the neighborhood of x. And what we really want, this local function operates on a node and its neighborhood. Think about the convolutional neural net, right? In that example, it operates on some sort of local neighborhood. So this red one is not the full image. It is just some sort of local neighborhood of this center pixel. In this case 0, in the next case 1, and then another one after it. So it operates on a local neighborhood. So similarly, for a graph, we want a function to operate on a local neighborhood, which means we care about this neighborhood feature set, multi-set of features in the neighborhood. And we define a local function g as operating over this multi-set xi and xni. So again, we're still in the definition land, trying to generalize these things from this tiny insight we got before into arbitrary graphs. So we can now construct these equivariant functions. Equivariant was order preserving, fxa, by appropriately applying this local function over all neighborhoods. And to ensure equivariance, we need g to not depend on the order of the vertices in x and I. So g should be permutation invariant. Okay, think about this. For we wanted to preserve the order of nodes, but for each node we don't care about the order of neighborhoods. Is this clear for everyone? Like in a node, I don't care which neighbor comes first or last because there is no order. But at the graph level, I do want this transition to be injective. Again, like 1:1. So for this node, there should be this corresponding output. I shouldn't be confused as to which node went to which output. If this is not clear, stop me. I'll pause for 30 seconds.
So
Mm-hmm.
this is with respect to a directed graphs, right? Or like because of acyclic graphs, like this won't be true, right? Sorry, this is with respect to directed graphs, right? Means like for or like other graphs as well, like this is true. Means
Like I said, the directed undirected graph basically relates to this adjacency matrix, right? If the adjacency matrix is triangular, or not even triangular, no mind, the triangular pertains to cyclic. But if the adjacency matrix is symmetric, that means, can I write here? How did Akash write? Annotate, draw. Ooh, okay. If the adjacency matrix is symmetric, this means undirected by definition, right? Because this is node x1, x2, x1, x2. If the matrix is symmetric, that means if x1 has an edge to x2, which is indicated by this one, and that also means x2 has an edge to x1, which is indicated by this one, right? This makes it undirected.
no, like I'm asking then like we won't have equivariance, right? For if we have undirected graphs, because for I'm not sure if this is right.
I think equivariance depends on
Means
the.
in this case, like we don't know which neighbor to consider. Like basically for
Okay. Maybe I should clarify exactly what is going on. So for each node, its neighbors will be considered, but for the other node also, this first node will be considered. Is that your confusion?
yeah, yeah.
Yeah, that
Like
that
I thought of it as like directed graphs only. Like so, yeah, this makes sense. Because if it's not directed, then basically we won't have like that equivariance mapping, right? Like for what I mean,
If it's not directed, then we won't have.
equivariance mapping. No, like sorry, yeah, we'll have. Sorry, I misinterpreted it. Like we have an order of nodes. Like I consider only one node. So like then basically like for either of the nodes we will have like the same one-to-one mapping, right?
Again, I didn't follow the last statement. For either of the nodes, we will have.
Like if we don't have like an order of nodes, like if we have just a directed node, right? So then basically if we consider like basically the single node, so then for that node we can have sorry.
Okay, let me give you a tiny example of how directed and undirected graphs will behave with this, because we still haven't. This is still the general case. Only thing that changes between directed and undirected is
It
this.
means like okay. So like basically my doubt was like basically let's say if we have like the center node like and there's a like a loop in this case. So then if we consider like basically a node, so for that node like we can have the other adjacent node, let's say. And if we consider the other node as well, then also we have like the same adjacent node like that. So then in that case there won't be any equivariance, right?
If you have a graph with
It's
just
like if we have a cycle, three nodes like this,
three nodes
let's
and you
say,
have a cycle.
and cyclic, yeah. Then for this case, do we have like equivariance?
Okay, do you have the same edge
Because in this
features?
case, for this node, like
If there are different edge features, then there will still be equivariance. If there are no different edge features, then all of them will have the same output, right? Sorry, not edge features, node features. Right now, I'm not even talking about edges. Sorry. Yeah, this update step to its next sort of latent state will depend on one, and will depend on this node and this node, right? Do you buy this? The update step for
yeah,
will depend on these two. Now, if they have the same features, um, let's first consider a case all of them have the same node features, right? That means this update step, this second update step, and this third update step. I actually drew it in reverse. If you consider message passing, then messages are incoming, not outgoing. Do you buy that all three of them will have the same representation?
yeah, like if they have same features.
If edge features are the same, they have the same representation. Then equivariance is still preserved because each node, it doesn't change the order. So operating on X versus operating on PX is not going to change because everything is the same for each row, right?
Yeah,
If they have different edge features, then again, by definition of this function f being equivariant, operating fpx will be the same as permuting fx, because and I'll explain why. Because this will now be a unique h1, let's say. I should really have my ipad for this. This will be a unique h2 because now they don't have all the same node features, and this will go to h3. So by definition of f being equivariant, it will preserve, if this is h3, h2, h1, it will preserve this h3, h2, h1 after being permuted. So this will still give you h3, h2, h1, and this will also give you h3, h2, h1. That is what we are saying. And if they are the same, then it will just be h1, 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 and order doesn't matter anyway because all of them are the same value. Is this fair?
Yeah, it's clear.
So regardless of cycles, regardless of arbitrary graphs, this order preserving is really up to this function f, which we want to be equivariant. All good?
Yeah, understood.
Okay. If not, like tell me again, I will rewrite all of this in a more clear manner, hopefully.
Like now I got it. I understood. Like if I was considering only single edge, but yeah, if we have order of nodes, then it is going to be unique. So yeah, there would be one to one mapping.
We don't have order of nodes. The only thing I'm saying is before and after
Mention.
is the same order, if that's what you mean by order of nodes.
Okay. Yeah, like that
Yeah,
one.
okay, okay.
Before and after order.
I just meant in the graph, like for the algorithm, there is no order of nodes. It can treat any node independently. Like it doesn't have to treat like first node first and like
Yeah.
third node third. It can, like your parallelization can do anything.
Okay.
So in engineering terms, you can give each of them a thread and they can compute the message updates and then update the state of that node. Okay. Although really like this is matrix multiplication.
Yeah.
Okay, cool. So we have defined this invariance equivariance on the graph. Thank you very much for asking me to clarify. That was very nice. We care about this local function operating on the node features as well as its neighborhood features. We want permutation equivariant functions at the node level because it doesn't matter what neighbor comes first and what neighbor comes last. It just matters that there is a neighbor or there isn't a neighbor. So in that case, we want invariance. At if we step one step back, then we do want to look at each node independently. So then we want f to be equivariance. Cool. So again, like just driving at this point of equivariance at the one level, invariance at the other level, and that gives us this sort of update step which I just drew out. I should actually have shown this diagram. Okay, so we want to calculate the update for node xb, and we want to calculate the xb will go to this latent state hb by considering all of its neighbors x a d e c. So x neighborhood of b, which also typically includes xb, just as the set of arguments. It can be a sum and it can be an average of all of its neighborhood node features. That is um, as simple an update step as g might be representing. And this average gives us this next node state, and then after b you can do the other ones in turn. um, yeah. So just to highlight what I just described verbally, um, you have certain inputs. You want to calculate the state update for xi. You put it in a graphnet. Graphnet computes this latent state hi, and then you can do one of many tasks on it. So you can do either just node classification because you have this update step for each node. You can actually do graph level classification by considering all of these latent states and some sort of permutation invariant function. um, or you can actually think of graphs. So what we really care in graphs are like this: if two nodes are connected by an edge, then there is some sort of similarity in some space, right? um, which means which makes this a very lucrative task to learn. So if you can learn link prediction, this function hi, hj, and eij, those three things are its arguments. So you want to predict whether there could be a link between two nodes given some edge features, historic data of edge features. Okay. So we've started with equivariant functions over graphs, then local invariance, which means for a node we don't care about which neighbors come first. We talk about graph neural net layers as diffusion, propagation, message passing. But like essentially there are three flavors of graph nets that most work will fall into. There are, well, there are more, like, but these three are really summarizing of many papers. So it's a very complicated slide and I will break it down so you don't need to understand everything right now. What you do care about is it's the same graph. All that is different in each case is this message that is passed. So on the convolutional case on the left, you can see that this is a constant C, A, B, C, B, D, C, B, E, and B, C. And there is a self loop. In the second case, we increase this expressivity of this function. So instead of just multiplying by a constant, and now you can look at the equations for the constant. So hi, this node state update, is a function phi of xi and a summation or some sort of aggregation of a constant times a function applied to each neighbor. So that is what it is doing, multiplying each neighborhood state by a constant after passing it through a function. In the second case, we now increase this expressivity. So we create this attention weight, where attention weight also accounts for the two node features, in addition to this node feature already being multiplied and being passed through a function psi for all of the neighbors of xi. And again, we have this psi function applied to the node features and its neighbor features. So just a little more expressive. And now this attention weight means it's a learnable weight. Um, and that can generalize to multi-head attention also, but I'll get to that in more detail. And finally, a very general form of saying the same thing is saying, look, I will calculate a psi for each set of neighbors. So recall that in both the previous things, you're basically aggregating the neighborhood somehow. Here, before that aggregation, you're applying a complex, potentially very complex function to compute a single message, which is specific to each set of neighbors. So this message passing is really generalizes both of these, because of course message passing can also be as simple as passing a constant, but it can also be as complicated as applying separate neural networks to each pair of elements to predict some sort of message. Anyway, this is expressing the convolutional nets in detail. What you want to take away from the slide is just that it is useful for homophilous graphs, and scaling up is insane. Like you can scale up to billion node graphs using simply convolutional neural networks. And it is useful when edges encode label similarity, which again, homophilous graphs. Um, okay. What you care about when it comes to attention weights is that it is useful as a middle ground. So you are slightly increasing the capacity, slightly compromising on the scale because you still have neural network based attention to calculate. There is this matrix of weight that undergoes updates. So edges need not be homophilous. So edges need not be of a similar type, but it's still like you're still doing the scalar computation of matrix multiplication on each edge. However, in this message passing stuff, now for each edge, you're doing something really complicated potentially. And so you don't want to apply. This is definitely not going to scale to billion node graphs, but it does allow you to be extremely expressive in terms of the functions that you use for modeling your messages. So most generic layer, it is a superset. Uh, it encompasses both the other models. But ideally, it's used for computational chemistry, reasoning, and simulation, where graphs are not necessarily very large. And um, I'm going to launch into this history very briefly because I've already run into an hour. And I do want to cover this next topic also, which really deals with where graph neural networks fail. So all of what I've said so far looks very clean, but it didn't start out like this. What it really started out with was people talk about node embedding techniques. So people said, okay, we have certain graph, we want to encode this U into this latent embedding Z in some sort of embedding space. Z is the same as what we call H, this latent embedding space. And at the time, it was as simple as a lookup table, so like a fixed flat embedding for the nodes. And then people start thinking about, okay, but like, what do you mean by a good Z? Well, a good Z really means if there is an edge between two different nodes, then you probably want their latent states, your Z or your H, to be close by. Oh, well, that defines this unsupervised training objective. If I have a graph, if I have its edges, then I can train it by saying, look, if there is an edge, I want to predict it to be 1. So with a binary cross entropy loss, this becomes an unsupervised training objective. After that, people came up with this, and like thinking about this, generalizing this to some sort of, we spoke about, if one edge is present between two nodes, then they should be close by. But think about like a neighborhood in terms of 3 or 4 edges away. So a graph that is connected to a node, that is node I connected to node J with 2 or 3 edges between it, should have a closer representation than node K with like 40 different edges connecting it to I. In the sense, 40 walk away, 40 hop away from I. I don't mean like 40 edges between I and that makes no sense. Anyway, so closer by, local patches, different ways of calling this, different ways of describing this. But essentially, what they said was this is a special case of random walk, right? Because if you go to a graph, you randomly walk among its neighbors, you see some sort of local neighborhood, you want all of their embeddings to be close by. And this actually dominated unsupervised graph representation learning before GNNs came around. So your node to vec, you might have heard of this at least, which, yeah, that arises from this line of thinking. And as it turns out, when you think about this, in GNNs, GCNs, when this convolution operation is essentially doing the same thing, right? Because if they have a lot of similar neighbors, in the diagram you can see HI in red and HJ in blue, having these purple-ish common neighbors and just like very little separate neighbors, then it does enforce similarity, because this average node state update, I say average, I really mean aggregated node state update, is going to have largely the same elements. Um, so now you're just sort of validating that, okay, graph convolutions do make sense. We have seen these in the past, do meaningful things, and intuitively they do optimize for the right objective. Cool. So actually, in practice, deep walk, this random walk thing, can be matched by an untrained convolutional graph neural network. So it is actually possible. It is actually seen that if you just do this, summarize these neighbors, then it is as good as a deep walk without training. Um, there are parallels between NLP and graph neural networks far deeper than I used to think. And he starts by just like comparing these things. So you have individual blocks that compose a graph. Similarly, you have individual words that compose a sentence. There are certain relationships between words, there are certain relationships between nodes. And then finally, you have these optimization objectives, which are almost the same, which means in NLP, you want to explore these relationships between words. You want to predict the next word, where it fits, which sort of ties into this link prediction task. You want to classify sentences, the sentiments on sentences, which ties into this graph level objective. And with recent progress, as it turns out, um, if you remember in NLP, earlier there used to be RNNs dominating, so the sequence to sequence approach was dominating. Um, um, sorry, the sequential approach to learning was dominating, where you considered the words occurring before to predict the next word. But later, this new approach came out, which said, okay, look, I want to consider this sentence as a fully connected sentence and then model the weights with a certain neural network, and then learn this. Basically, I'm getting at attention. Um, Anyway, when attention came about and this masking of attention came about, someone sat down and thought about it and said, well, wait, this transformer stuff, which relies completely on attention, is essentially a fully connected graph attention network. And you're just masking out some of it at each learning step with this positional embeddings. And this is actually a great article. It has very nicely summarized math. So if you're familiar with the query key value stuff for attention, it you will actually enjoy reading it, and it takes 5 minutes. So definitely read this paper by Joshi, Chaitanya K. Joshi to be precise. Okay, so clearly there are a lot of other fields that have been implicitly using these same approaches that we see now in graph neural networks. And before I go into um, the limitations, I sort of want to talk about these interesting observations on graph neural networks. So, if you are familiar with how CNNs evolved a long time ago in 2012, we had this ImageNet challenge come out, and this convolutional neural network. ImageNet came out before, but CNNs really destroyed the challenge compared to other approaches early on, which led to their growth. And early models had shallow layers but large filters. Later, the progress took us in a direction that led to deep models with very shallow filters. Um, and so you people started examining why this is the case, why these work better, and they came up with these ideas of compositionality. So an edge detector, after a few layers, combines feature maps to learn your nose. After a few layers, combines feature maps to learn the eyes and nose and lips. After a few layers, combines feature maps to learn your hair, your face. So there is this idea of compositionality. But that actually doesn't work for graph nets, which, and we will see this later, they're equivalent to this Weisfeiler-Lehman test. It was shown they cannot count triangles. So you cannot actually compose nodes into this shape and count the number of shapes in the graph, sort of. Um, but it's quite counterintuitive because, like, if you start thinking about convolutions, you're like, okay, they're building up by considering one hop neighbors, then two hop neighbors, then three hop neighbors. Because think about it. So, like, a three hop goes, the messages are passed in one iteration, second iteration, and then third iteration. So, you would probably think of it as okay, it probably builds up some picture of on a global level, but that doesn't seem to be the case. And the second observation, evidently, stacking layers in graph nets does not help. And so what you're seeing here is this, what you want to see is the first line highlighted in yellow, where the 64 layer graph net has almost half the performance of the 2 layer graph net. And that's very weird. But the explanations for it include two things. Firstly, this aggregation operation is leading to some sort of feature smoothing that makes you lose discriminative power. So over multiple layers, you're creating too much of a smoothing effect, and that might be an issue. Second, there might be this information, there is shown to be this information bottleneck problem, which, so this information bottleneck problem is essentially saying in real world graphs, I have a lot of neighbors, but I don't have a lot of like um, in this case, you can see the levels in the diagram. So if you rearrange the graph, there aren't so many levels as the number of neighbors. So neighbors grow exponentially. And in these graphs, it is very hard for more information to be passed through in a single node step update. So there is a certain bottleneck due to this structure of these graphs. And that is explored more in this paper. And this is all from Michael Bronstein's talk. Previously, we saw material from Petar Velishkovich's talk. Um, I would highly recommend like just going to YouTube and looking up those talks, and I've also provided links to those. In addition to just like current work and past work, they also have nice Q&A sessions with like future perspectives and like where the field is going, which should be helpful in seeding research ideas. And GraphNets have a lot of software and libraries, but I'll get into that. So basically, interesting observations from GraphNet land. And finally, we are ready to jump into the limitations. So I will now proceed to tell you what I previously told you was right might actually not be right. So remember how we spoke about the fundamental question where we want to determine whether two graphs are isomorphic. So these two are clearly not isomorphic. They have the same number of nodes, but they do not have the same structure. And can the question is, can a graph tell them apart? Like, can they map them into different representations? Which is the converse of the isomorphism question, which is what if two graphs are the same structure, can they will they produce the same output? So graph isomorphism test, like we discussed, no polynomial algorithm exists for the general case, but there is an algorithm that does approximately okay. So the question then is, how well can GNNs perform on this test? And if you it requires a sort of deep think about how GNNs capture the structure, and goes back to our invariances. Um, Before that, though, let's look at computationally what is happening. So in the graph on the left and the graph on the right, we create a sort of computational graph for each fe- node feature update, node state update. So from the X to the H, that is what this computational graph is representing for each node. And out here, the nodes are labeled just for our understanding. There is no real order in the graph. So for the first, and all of the features are equal in both the graphs. So all of them are colored yellow, sort of indicating that the feature vectors are the same. So for the first node, you're combining two of its neighbors, 2 and 4. For each of 2 and 4, and hopefully this ties into Jess' question that he raised earlier, like what are these state updates and cycles? For each 2 and 4, they have two neighbors each. So they compute these state updates. So that is how the state update for 1 occurs. Similarly, there is a computational graph for the state update of 2, computational graph for the state update of 3 and 4, which, as you might see, is the same in each case, because all of them are this is a regular graph. I think regular is, yeah, okay. However, for here it is a bit different. For 1, now it is connected to 3 different nodes, and in turn 4 is not connected to any other node, so that's just 4. Well, 4 is connected to 1, so that's just a single node, and each of 3 and 2 are connected to 2 other nodes. So those are two state up computationally, 2 feature averaging. Yeah, okay, 2 neighbors each. And so you have the computation graphs for the others as well. And your goal, really, again, to express your question very concretely, is, if you call this the rooted subtree structure, can the graphs tell them apart? So in this case, the color is indicative of discriminative ability. In this case, color red indicates all of them are the same. Then you have blue, purple, and green, indicating there are 2 of them have the same rooted subtree structure, and then 2 of them have different rooted subtree structures from these other 2. So your question is, can the graph identify this? And what you're saying is, I want injectivity. And what was injectivity? It was saying, I want different elements to be mapped onto different output values. I do not want a many to one relationship in terms of this function, because if this is a many to one, then this blue and green might actually be mapped to the same value by passing it through this function. The function, imagine the function as the G that we spoke about, which maps your nodes and its neighborhoods into a certain output. So here they call it the F, doesn't matter. But yeah, we want injectivity for our graph to be able to discriminate between these two non-isomorphic candidates. And one way to think about injectivity is if at each step you have injectivity, then the entire function will be injective, which means it can, if it can tell apart these different state updates, then it can tell apart this for the entire graph. But now remember what he spoke about when he said aggregation functions right at the beginning, like these aggregation functions help us out and we really use them and need them and so on and so forth. Well, as it turns out, if you have multi sets, then can someone tell me if blue is the max of yellow and blue, then what will be the max of yellow, yellow, and blue? I mean, everyone knows the answer, everyone's just afraid to say it out.
It would be blue, right?
It's still blue, yeah. If blue is the max of yellow and blue, blue will be the max of yellow, yellow, and blue. So if your aggregation function is max and your neighbors are yellow, blue, and yellow, yellow, blue, will you have this injectivity? Again, you know the answer, just put in the effort to unmute. You have 50% chance of being right. It's a yes or no question. Okay. I haven't been clear enough. Okay, so what we are talking about is the question is telling apart these two graphs. Why do we care about this? Because we want to check the power of graphs, of graph neural networks. We know that these two graphs are not isomorphic. How do we know? Well, we looked at the rooted subtree structure. We saw that these state updates are different. They are resulting in different node values. The question is, can our graph tell these things apart? If a graph is to tell these things apart, it needs injectivity. What does injectivity mean? It means at every level, we can examine these node state updates and say, okay, look, this is different. This rooted subtree structure is different from the other rooted subtree structure. How we do that? By looking at neighbors at each step. So we looked at the neighbors of one, then we looked at the neighbors of the neighbors of one, then we go on and so forth, keep looking at the neighbors until we see a difference. Okay. Then we spoke about, okay, but what like computationally what happens in graphs? Well, in graphs we have these aggregation functions. These aggregation functions operate over the neighborhoods. What happens in the neighborhoods? Then maybe I should go to the slides. So the discriminative power of graph nets can be characterized by that of these multi-set functions. So these aggregation function over multi-sets. Well, what happens in graph convolutional network? I didn't want to go into this much detail. Um, yeah, I want to first stick to this example, right? There are two different neighborhoods of two different nodes, okay? And our goal is to discriminate between these two nodes based on their neighborhoods. Visually, you and I can see that these two neighborhoods are different. By two neighborhoods, I mean one has yellow blue and the other has yellow yellow blue. Now my aggregation function is max pooling. I'm looking at the max. We discussed that the max cannot tell these apart. The question then is, can the graph neural network discriminate between these two graphs?
It would be not able to distinguish, right? Because we are getting the same aggregate for both the graph, multi-set system.
Exactly. Thank you very much. So clearly, like this won't be able to tell apart these two nodes based on their neighborhoods, and that is a problem for us because that means this graph is not powerful enough to discriminate between this very simple case. And we have been throwing graph neural networks at so many different problems, assuming that they have all of this capacity and they can solve all of these problems. And funnily enough, we have been getting results also. So we really need to rethink, like before we go around touting, oh, graph nets are the next new thing, that what is the power of a graph? And so Now we can jump into like properly analyzing graph convolutional networks and this very popular random sampling algorithm, graph sage, um, in terms of what is going on. So turns out graph convolutional networks use mean pooling. Now for mean pooling, you probably already see where I'm going here. The average of yellow and blue is, let's say, green. Can you tell me what will be the average of two yellow and two blue?
It's going to be the same.
It's the same average. So again, we have a problem with mean pooling not being able to tell apart these two neighborhoods. And again, this ties back to what we spoke about. It is not injective. It is not mapping one to one. It is mapping both of these values to the same output, which is many to one. Another example of graph sage, which we already spoke about, uses max pooling. So if blue is the max of yellow and blue, blue will still be the max of yellow, yellow, blue, and blue. So again, we have a sort of problem. And these folks then present this idea of doing injective multi-set functions, by which they mean we our functions can tell apart these neighborhoods, at least like more than the current graph convolutional and graph sage approaches can do. And they say, okay, we use this idea of sum pooling, um, which is, yeah, I mean, you can read their paper for more details, but the idea is just you sum all of it after applying a function to each of it. And this function f is injective itself, so it maps one value to one value. um yeah, it's not really very complicated, but you see why, like, you need to sit down and think about these problems to come up with these corner cases and then come up with solutions to the corner cases. And they wrote this paper called graph isomorphism network, and we can now tell these two examples apart. We have an injective function, neighborhood aggregation is injective now. Yay. They were pretty influential in the field, so kudos to them. And they, yeah, you're basically just saying, again, go back to that example. Now we have injective graph pooling, so we can look up what is going on in the graph and we can tell it apart. um I want to talk a bit about the WL test really quickly. But you remember how we built this graph by examining neighbors at each stage? Well, that is essentially what the WL test does. So what you're doing is, at each stage you're looking at neighbors, comparing it with the other graph, seeing if there are any differences. If not, then they're both similar. Again, you look at the next stage of neighbors, compare these two graphs, and by compare I mean each node is, you want to find this mapping of each node into the other graph, because order, you don't have ordered nodes. You just have a collection that, oh, I have 5 nodes, one of them has 2 neighbors, 4 neighbors, 7 neighbors, 6 neighbors. If the other one has 5 nodes, one with 7 neighbors, 4 neighbors, 6 neighbors, and 2 neighbors, this is still one to one. So you can't tell these two graphs apart, right? Because these numbers match up, the order does not matter. Then you have to go to the next step. Again, look at these different neighbors, number of nodes, number of, yeah. Sorry, Jay, go ahead.
Um, Somewhere in this year also there can be possibility, right? Where we see could get like non-injective graphs as injective graphs only in a way. Means like, let's say the sum of nodes for both the cases equivalent, then or like, means like nodes can be different but the aggregate sum at the end leads to the same value for both of the graphs.
Nodes can be different, but the sum can be the same value. This is true. However, they think they control for it by adding an injective function. Nodes can be different, but they can get sum to the same
Means
value.
like,
One
let's
is
say
smaller, the other is correspondingly more.
function is, sorry.
No, I think I see what you mean. I don't remember, like, I haven't read the paper, so I can't really answer very informatively. But to me, that sounds like a corner case they probably would have handled in the paper. So my explanation might be wrong about exactly what they're doing. Like you're saying, if you reduce a node by a certain value and increase a node by a certain value, then the sum will still be the same. So, like, what are we really changing? My point is with this MLP, they probably map these unique values such that you don't have, yeah, like you don't have the same differences. Like if one increases by 5, the other will decrease by 5, but mapping these won't change them by the same value, and therefore it will still be different. Is that I buy
But
it to argue
in
that
this case,
numbers.
like, if we increase,
Sorry.
sorry, can you repeat? Like,
Right. So
no.
I assume you
Can
are
you
saying,
repeat like last time your audio?
yeah, I assume what you're saying is if we increase a node by a certain value and decrease a node by a certain value, on average, the it will still have the sum pooling will still be foolable, right?
Yeah.
My answer to that without having read the paper is if I was doing this, I would think of the neural network. So this function f maps this yellow to a certain value, right? Which means that difference in 5 won't remain a difference in 5. It will change to something else. And it maps this blue to a different value, which means this reduction in 5 won't remain this reduction in 5, it will change. So I think you can find some adversarial examples where you tweak the differences to match, but it will be hard to do that.
Okay.
Cool.
Okay.
Sounds good. Um, okay. Where was I? Yeah, I was here. I was explaining how we check for isomorphism. Well, the Weisfeiler-Lehman test checks for isomorphism the same way. First, count the number of nodes. Okay. Then look at all of the neighbors for every node. Count these numbers of neighbors and see if the sets are the same. Again, count the number of neighbors at that stage. Look for each neighbor, look at its neighbors, and iteratively build that tree. So you can imagine this gets extremely expensive really quickly. So you really can do this for 2 or 3 levels and then your computation blows up. Which is why, like in the general case, it's not possible. Like we don't. This is an NP complete problem. You probably get some sort of mathematics award if you actually solve this in graph theory. So what they show basically is their network, this graph isomorphism network, where they use sum pooling. They show that this is actually as discriminative as this test because it builds its graph in the same way, similar to graph pooling. Yeah. Anyway, they are operationally equivalent. That is your takeaway from here. Graphs that are distinguishable using this Weisfeiler-Lehman test are graphs that graph isomorphism nets will actually distinguish. And they show nice results, but I'm going to skip over them right now and go back to my slides where I just have 2 more things to say. One is the software libraries. Like I said before, please try experimenting with these things. They have really nice examples pre-built for you. It does not take a lot of compute for graph nets. There are very nice available data sets and benchmarks to look at. PyTorch geometric I would particularly recommend because I have used it and I've found it to be very nice. I like the developer. He responds very actively to even issues and requests and even comments. That's really nice. Like for me, that's indicative of a healthy research environment using this sort of tool. But anyway, I've used the other tools also. I haven't actually used JRAF. I think JRAF should be good because JAX also has a very active research community around it. DGL, I liked it. They had nice examples, but I haven't used it, so I can't comment. TensorFlow, again, not used. I kind of looked at the GraphNets library, didn't very much enjoy it. But yeah, that was many years ago, so who knows. These are some sorts of links you might want to look at. There is actually a graph representation learning book by Will Hamilton, and these are some talks that I used to actually compile this. I would shout out to these people again. Thank you very much for making the resources available online. Most of my slides have been built from their images and stuff stolen from their lectures. So I will pause here, stop here and take any questions you might have. Okay, seeing none, let's stop recording and then talk.